In this problem, we're going to figure out the non-standard cell potential for a reaction involving copper and silver. The first thing we need to do is construct a spontaneous cell involving the two half reactions. Remember, one thing must be oxidized and the other thing must be reduced, so we can't use the two half reactions by simply combining them currently. We need to make sure that we're left with something that has a positive cell potential. Because of that, I'm going to write the copper reaction backwards to ensure that I get an overall positive cell potential when I combine these two reactions. So now I've got two electrons coming out of copper because it's being oxidized. I've got silver ion getting reduced, and I need to make sure my electrons are going to cancel out, so I'm going to multiply everything in silver by 2. And remember, when you multiply everything in a reaction, nothing happens to the actual potential, it just stays the same. So when I combine these two equations, I get copper plus 2 silver ions going to copper 2 and 2 silvers. This cell potential is going to be equal to 0.8 minus 0.34, giving us a cell potential of 0.46 volts. Now that's the standard cell potential, but we're not at standard conditions. So we have to use the Nernst equation. The Nernst equation allows us to calculate non-standard cell potentials. So now that we've got our standard cell potential, we can use the Nernst equation to calculate the non-standard cell potential. Recall that this non-standard cell potential, E, is equal to standard state cell potential minus the gas constant R, the temperature T, over number of moles of electrons times Faraday's constant times the natural log of the reaction quotient. Well, what is the reaction quotient? This goes back to the equilibrium chapter when we talked about reaction quotients. So in this particular case, we're going to get E cell minus RT over NF ln of products over reactants, so copper 2 all over silver. Now we can plug and chug. 0.46 volts minus 8.314 times the temperature in Kelvin, so 25 degrees Celsius is 298 Kelvin, all over the number of electrons transferred, 2, times Faraday's constant, 96,500, times the natural log of the copper concentration, so 0.0034, all over the silver concentration, 0.34, quantity squared. Going through and solving for that, I get 0.51 volts. And that's how we use the Nernst equation.